Our second talk of this afternoon, we'll have Harold Williams to tell us about canonical basis for Coulomb branches.
Great, thank you. So is the audio good? Right, so of course, let me thank the organizers for their work and for the invitation to speak here. I think essentially every project I've worked on has been influenced by Sasha on some level, so it's a particular pleasure to speak on the occasion of his birthday. Specifically today, I'll talk about some joint work with Sabin Kautis. So a quick apology to some of you. So this project has been an especially long time in the making. So I gave essentially the same talk a few times already at the start of the pandemic, but I don't think I ever gave this talk with Sasha in the audience. So hopefully that will make it a little more forgivable. So the goal of the talk, I'm going to describe a certain tensor category of what I'll call causal perverse coherent sheaves. This is going to be a tensor category associated to a pair of a reductive complex group G and a complex representation N. So I'll explain that notation a bit in a moment and try to justify the terminology as the talk goes on. But let me start by giving a few motivations for discussing these categories. So I'll kind of give three, which in the spirit of the conference, maybe I'll label as physics, geometry, and algebra. So that distinction will be a little bit artificial. So the first one is that these categories are meant to provide a mathematical definition of a certain physical notion, which is the category of half BPS line defects in a 4D n equals 2 gauge theory with polarizable matter. So this is a certain class of monoidal categories that are anticipated and studied in the physics literature, specifically by Kapustin-Solina and Gayatu-Mornitsky. And they laid out various kind of expectations for interesting features that these categories should have. And in particular, a basic feature is that they should have a good notion of an irreducible object. And this leads us into the second point, which is that their irreducible objects should induce a canonical basis in the associated Coulomb branch. So specifically the 4D or K-theoretic Coulomb branch, which following which was given a mathematical and algebra geometric definition following Broderman, Finkelberg, and Nakajima. And I'll recall their construction in a minute as well. And then the third kind of general, and so these quantized Coulomb branches are of interest for a number of reasons besides their physical origin. And all right, so the third kind of general motivation is that these categories are going to turn out to be cousins of other tensor categories, which are of kind of independent and ongoing interest in representation theory. So specifically the categories of representations of affine quantum groups and of quiver-Hecke algebras. So we'll see various structural features as we go along. Any general questions? All right, so before I dive into the definition, which will involve this BFN construction of the Coulomb branch, let me just try to lay out in an example what one of these categories looks like up close. So in general, we can't give such an explicit picture, but in the case of here, so here we have G, the group is GL2, and the representation is just the defining representation of GL2. And this is some kind of artist's rendering of what this category looks like. So first of all, so I've said that these are all going to be tensor categories. They're going to have a good notion of irreducible or simple object. And in this case, the simple objects are just going to be labeled by a pair of a weight and a co-weight for the group up to the diagonal action of the Weyl group. So those are the labels of the irreducibles. And then what is depicted in this picture are more specifically the prime simple objects, which means exactly what you think it means. So they're the simple objects, which are not units. They don't have a monoidal inverse. And they can't be written as a product of other simple objects unless one of those is a unit as well. So these are kind of so we have this class of prime simple objects. And we can further classify these according to whether when you take their square with respect to the monoidal structure, you again get a simple object or not. Okay. So in this case, so over on the right part of this picture, we have the ones where these are the simple objects where the square is not simple. And these are all of the forms of the little subscripts are the co-weight and weight labels. So those simple objects all turn out to be of the form, their co-weight label is 0. So they're just labeled by a weight of the group GL2. And in fact, those objects collectively form a monoidal subcategory, which is equivalent to just the category of finite dimensional representations of GL2. So we have this big kind of complicated monoidal category, but sitting inside of it, I have this little piece that just looks like the category of representations of GL2. And of course, you take two random representations of GL2, tensor them together in the usual sense. That's not again going to be an irreducible GL2 representation. Meanwhile, we have this whole other collection of objects, which is quite different. So these are the ones again where their monoidal square is again simple. So following the terminology of Hernandez-Leclerc, I'll call these the real simple objects. And I've depicted these as the vertices of a certain graph. And what this graph is communicating, so an edge in this graph indicates that the simples at either vertex commute, in the sense that when I take their, so here I'm writing the monoidal operation as this little star. And so I'm saying that these two objects commute if their product in either order is isomorphic. So implicitly, the corollary here is that in general, if you take two random objects and you take their product in the two possible orders, you'll get different results. Okay, so it's a special case when two things actually commute. And again, if you're kind of familiar with other parts of representation theory, say this is a feature of the category of finite dimensional representations of a quantum affine algebra. And it's this fact that you take tensor products in opposite orders, they're not generally isomorphic. And of course, that's very different, say, from representations of an ordinary group or even a finite type quantum group. So that's some kind of flavor of this, this tensor category. And the most basic situation where this asymmetry manifests is when you take the product of, you look at two adjacent triangles in this picture, and you take the objects at the opposite vertices of that pair of triangles. So here I have a little square that's formed by the P20 is the top vertex there, and then the opposite thing, P-10, that's on the third row down. If I take the product of those two objects in the two possible orders, we get non-isomorphic results, but in a very controlled way. So there turn out to be a pair of kind of opposite exact sequences with the same outer terms, but with these two products as the distinct middle terms. So in particular, if I look at the Groton decrease, so I look at the class of these in K0, both of those products have the same class, even though they're not isomorphic. And the relation that's implied in the Groton decrease of this category, those of you familiar with the theory, with cluster theory, will recognize this as the exchange relation for a certain cluster algebra. And collectively, all of these exact sequences give the Groton decrease of this category the structure of a cluster algebra of type affine A2. And again, that will, for those of you familiar with the formalism, which don't worry if you're not, I'm not going to invoke it, but that is also kind of encoded in these little quivers that I've superimposed on the triangles of this graph. So that's a kind of picture of what kind of a category, what this thing looks like up close. Any questions about this picture? All right. So
Actually, is there something special about the upper right corner, or is it just missing an arrowhead?
it's missing infinitely many edges.
I mean,
Oh, sorry, the upper right.
the upper right corner, there's two blue lines without an arrowhead on it.
What's special about that triangle was that that's the triangle where I made a typo in the drawing.
Ah, okay.
Yeah.
Thanks.
Okay. All right. I like questions that get me laughs, by the way. So, all right. So on to the actual definition of this category. And as I said, this is going to build on this construction introduced by Braverman, Finkelberg, Nakajima. So first, some notation. So throughout the talk, we'll write K for the field of formal Laurent series in a variable T, O for the subalgebra of formal power series. And then associated to group G, we have the affine Grassmannian Gurr G. So that's the quotient of the group of G-valued formal Laurent series by the subgroup of G-valued formal power series. So then associated to the representation N, what BFN tell us to consider is a triple of infinite rank vector bundles over the affine Grassmannian. So one I'll denote by V1. That's the trivial N sub O bundle over G. So here again, N sub O, that's the space of N valued formal power series. That of course sits inside the bundle, which I'll call W. That's the trivial bundle whose fibers are the space of N valued formal Laurent series. That's G cross N sub K. And then sitting inside that, there's a twisted bond, there's a non-trivial bundle whose fibers are also isomorphic to N sub O. And that's this, I take G sub K times N sub O, and I quotient by the diagonal G sub O action. So V, that again sits naturally inside W. And so what the definition of the Coulomb branch is that first you consider the space RGN, which is the intersection of V1 and V2 inside W. That continues all of these spaces, and in particular their intersection continues to have an action of the group G sub O. And so the K-theoretic Coulomb branch algebra is just the equivariant, G of O equivariant algebraic K-theory of RGN. This has a natural ring structure, natural convolution product related to the convolution product of the affine Grassmannian. Let me not worry about giving the explicit definition of that. All right, so there's the definition of the space. And let's talk about the simplest non-trivial example where N is non-zero. So this is the example where N is just the one dimension, where I should say where G is C star, and it's just acting linearly on its defining representation. So this is RC star C. Okay, so what is GER C star? Well, first of all, GER C star is up to passing to it's basically a countable disjoint union of points which are indexed by the different powers of T. More precisely, this is its reduced locus, but whatever. So here's GER C star. And now let's talk about what W is. So W is, so I take the bundle over all of these points, whose fiber over every point is a copy of N sub K. So here N is just C, so N sub K is just K itself. So this is just the trivial K vector bundle over this countable set of points. So K is, it's an infinite dimensional vector space with the basis indexed again by the integer powers of T. And I'm going to depict each of those copies of K as just a line with a bunch of beads on it, one bead for every element of this basis. So altogether, RC star C, I'm going to draw as a countable disjoint union of a bunch of lines, each with countably many beads on it. So that's my picture. So there's W. And now we're told to intersect these two spaces inside W. Okay, what is V1 in the picture? Well, it's just in each of these fibers, in each of these connected components, we take the span of all of the non-negative powers of T. So in other words, I take all the span in each component, I look at the span of all the beads that are above that horizontal line there. That's V1 as a subbundle of W. And then V2 is similar, but what it means, what that twisted kind of bundle means is that in the connected component labeled by T to the N, I take the span of all the powers of T whose exponent is bigger than or equal to N. So in the picture, that means in each component, you take the span of all the beads that are above that diagonal line there. So there's V1, V2, and W. And so you take their intersection, and it's in each component, it's the span of the beads that are above both those lines. So the beads that are highlighted in red there. Questions about the picture? All right, so here's a remark. This remark is completely irrelevant if all you're interested in is defining the Coulomb branch algebra, but it's going to be absolutely essential in what we're about to do, which is going to be more specifically about coherent sheaves on this space. So the fact that V1 and V2 don't intersect transversely in W means that this intersection naturally has a derived enhancement. And that's really what we want to consider when we talk about coherent sheaves. So what does that mean specifically? It means that really each of these, let's say if I zoom in on a single connected component, so it looks like this is just an infinite dimensional affine space. So an affine scheme, which is spec of a polynomial ring and countably many generators. But actually the derived intersection is something that's a little bit enhanced by that. It's a kind of scheme whose coordinate ring is now a non-positively graded DG algebra. Which in this case, we can kind of simplify things and say, well, it's again a kind of derived affine scheme whose coordinate ring is a polynomial ring, but now on countably many generators in degree 0 and countably many generators in degree -1. Or geometrically, we might say, well, this is the product of a kind of normal classical infinite dimensional affine space. So what's what I've written over on the right-hand side is T to the n plus O. So that's a subspace of O. N plus is the max of 0 and n. And then it's kind of, we should really think each connecting component is the product of that with another infinite dimensional affine space. But now this is an affine space in degree 1. So it's an affine scheme, a derived affine scheme, whose coordinate ring is generated by elements in cohomological degree -1. Okay. And that kind of second factor there is exactly capturing the failure of V1 and V2 again to span W. So if you like that second factor, it's again an odd kind of affine space, but it's spanned by the beads that are below both of those lines in the picture. So it's kind of the span of those blue beads. And so in a second, so again, this is important if we want to talk about coherent sheaves. And just to be totally clear, so if I talk about coherent sheaves on RGN, really the derived category of coherent sheaves, say in this kind of essentially simple example, coherent sheaf on RC star C, that's going to be a finite sum of coherent sheaves on finitely many components. A coherent sheaf on an individual component, that's going to be a DG module over this DG algebra, such that its total cohomology is finitely presented over the degree 0 cohomology of the algebra. That's what we'll mean by the derived category of coherent sheaves on RC star C. So that's kind of something that we'll keep in mind in the background. And the only thing, the kind of main comment to make about that before moving on is just that once we made this remark and kind of filled in this blue part of the picture, notice that the picture acquired a symmetry that wasn't there before. So there's a symmetry now between the red part and the blue part of that picture. That will come back later, turns out to be connected to the symmetry of those opposite exact sequences on the previous slide. Any questions? All right, so to return to our kind of framing in terms of this physics motivation. So if we take as our starting point, well, there should be some category, let's call it CGN, with the property that it has a bunch of irreducible objects. The Grothendieck ring of this category should be the Coulomb branch algebra. So it should be what we're told by BF and N is the equivariant K theory of RGN. And the irreducible objects in CGN should define a basis in this Coulomb branch algebra. So the natural mathematical guess from the point of view of homological algebra is that CGN should be the heart of a non-standard T structure, a finite length T structure on the derived category of coherent sheaves on RGN. Okay, so the key kind of, what do those words mean? The key thing is, the key point is that we expect this, the natural expectation is that this is some abelian subcategory in which there are finite composition series. So every object has a finite length composition series. That's the property that guarantees irreducibles give you a basis in K0. And it should have the same K0 as the whole, as the ambient triangulated category. So that's the kind of natural guess again. It can't be so the derived category has a natural standard T structure. That can't be what we're looking for though, because it doesn't have a good notion of irreducible object. It's not finite length. All right, so we want to find, our guess is that we're looking for some CGN of this kind. And we have a guiding example, which is the case n equals 0. So in the case n equals 0, RGN is just the affine Grassmannian itself. And we have the category of perverse coherent sheaves as a natural non-standard T structure. So this was introduced and studied by Bezirkovnikov, Finkelberg, and Virkovich. And without giving you the full definition of this category, let me just tell you the simplest example of an object in this category. So G is some big infinite dimensional object, but at least if G is nice, it will have some, let's say if G is GLN, then there will be some closed G sub O orbits. These will just be ordinary finite dimensional projective varieties. So if I take one of those closed projective varieties, well, for every integer n, it has a line bundle O of n. I can take that line bundle O of n, I can push it forward. Now I have a coherent sheaf on G. It's a typical example of what a coherent sheaf on G looks like. So it's supported, it has some finite dimensional support. So I take this push forward of O of n, and I shift it cohomologically by half the dimension of the orbit. That's the most rudimentary example of an irreducible perverse coherent sheaf. So again, this has kind of all of the features we want to that kind of tell us, this really seems to match up with what we're told by the physics literature should be this category of defects in this pure G gauge theory, as one would say. So in particular, Bezirkovnikov, Finkelberg, and Mirkovich, so they proved that this is a finite length abelian category. It's closed under the natural convolution product, so really is a tensor category. It's closed under various dualities. And there's a class, it's hard to describe a kind of general irreducible object, but there's at least a clear labeling of them, so we can classify them. And they have this labeling that we already saw a few slides ago. They're labeled by pairs of a weight and a co-weight for the group up to the actionist Weil group. So those are, again, some kind of some key things one wants. And then we studied this category more in previous work, and in particular fleshed out some of these connections to cluster theory and R matrix theory that were, again, anticipated in the physics literature. So bottom line, for n equals 0, one has a good kind of mathematical description of this putative category of line defects. Any questions? All right, so what about so what could CGN be when n is non-zero? I mean, the first thing to say is that for various reasons, the perverse T structure does not naively extend in a useful way. So we have to do something kind of really different in the n equals 0 case to get a good answer. So let me try to give you kind of two descriptions of an answer in this general case. And one thing I'm going to have to do at the outset is I'm going to make an auxiliary choice. So I'm going to choose a central subgroup of G, which is isomorphic to C star, really just a central co-character, which acts on n with weight 1. Okay? If G doesn't match, so if G is GLN, say we looked before this GLN and CN example, in that case, we could just take the diagonal of GLN. And in general, if I don't have such a subgroup handed to me, I could just adjoin one. So I just extend the equivariance to be the product of G and C star. That's not going to, that'll be kind of a sufficiently mild change that we're kind of happy, one is kind of happy to work with there. So, oh, thanks. Right. So given this, this central C star, one thing that we get out of this is we have a weight decomposition of the derived category of coherent sheaves. I can, given a coherent sheaf, I can look at the action and equivariance. Yeah, what's going on? Okay, well, I'll keep talking. We'll see if it keeps happening. Yeah, so I have a block decomposition now of this derived category according to the weight by which C star acts on a coherent sheaf. And I can use this block decomposition in turn it lets me define a kind of twisted version of this perverse T structure. So I'm going to take the block of this derived category in weight n, and I'm going to shift it by cohomological degree n as well. So this gives me, so this is a kind of very simple regrading autoequivalence of this derived category. And I can I can basically just translate the perverse T structure under this regrading autoequivalence. And then the kind of implicit characterization of a T structure which seems to do everything we want is the following. So there exists a unique T structure on the derived category of equivariant coherencies on RGN, such that the following functor that has source, what we just said, has target the derived category of GO equivariant coherencies on GERG, such that this is T exact with respect to this twisted perverse T structure. And what is this functor? It's just, well, RGN, that's defined as it's defined as a subspace of what we wrote as V1 before, this trivial bundle GERG cross NO. So I can take a coherent sheaf over on the left-hand side, I can push it forward to this middle term. And then I can restrict it to the zero section. I can pull it back to GERG along the inclusion of the zero section. So that gives me, again, some functor, some exact functor between these two triangulated categories. And the claim is that there's a unique T structure, which is T exact for that perverse T structure. And this is what I'll denote its heart by this symbol KP co of RGN. And then theorem, this has lots of the properties one wants. Yeah. Yeah.
Why is this theorem cool?
Well, it's a okay, maybe I should almost write, so the first theorem is more of a definition than a theorem. The second theorem is a real theorem. And the second theorem is what says that that T structure that you just defined is actually interesting, okay? Because it does all of these things that we set out wanting to do. In particular, it's a finite length T structure. And so its irreducible objects indeed give us a canonical basis in this Coulomb branch algebra. It's closed under convolution, duality. So it's a canonical basis in the usual sense one means. You take the product of two elements in this basis, it'll expand as a positive sum of other elements of the basis. It has renormalized R matrices, which is again some extra structure of interest. And we can classify its irreducibles. And they're in bijection with those of the category that we kind of had on the previous slide. So the category of perverse coherency is just on GERG. As with the perverse case, a general object in here I really have very little to say about. It's hard to get one's hands on it explicitly. But again, in this case of a closed orbit, it's kind of easy to say what are some basic examples. So here, if I have a closed orbit in GERG, so one usually I should have said, these are going to be labeled by certain co-weights. Let me call such a co-weight lambda. If I have closed orbit GER lambda, I look at I look at the restriction of RGN to GER lambda. I can look at, again, that's some derived thing, but I can look at the classical part of that derived thing, or just take the classical intersection, take the structure sheaf of that, or really take the pullback of O of n from GER lambda up to that big scheme, and now push forward that with the same equivariant shift as before. So that's a simple, that's again, the most elementary example of an irreducible object in this category. Questions? All right. So I kind of asserted the existence of this. I characterized a certain abelian category by saying such and such functor is T exact with respect to some, T structure that was already a bit mysterious. What does this category look like? Well, I can try to say a bit more explicitly what it is as follows. So let me go back. So we again have these the bundles V1, V2, and W. Let me go ahead and use the same notation for their sheaves of sections, and then let me write V2 perp for the sections of W dual, the dual bundle of W, such that when I pair them with a section of V2, I get 0. So here's another sheaf on GERG. And now I'm going to look at the following algebra, or the following sheaf of algebras. Let me take V2 perp, put that in degree -1, take V1, put that in degree 1, take their direct sum, take the tensor algebra of that. So one of those generators looks like a pair of phi V, where phi is a section of V2 perp, phi is a section of V1. And I impose the relation that the square of that is equal to the value of phi on phi. So in other words, this is a sheaf of algebras whose value at a point in the affine Grassmannian, let's call that point G. So G here is a formal Laurent series valued in the finite type group G. So it's an element of G sub K. And so I can associate to that element, I can look at, I can first say, okay, I have n sub K and I have n dual sub K. That naturally has a bilinear form given by pairing and taking residues. I can look at the subspace of that given by n dual sub O and G times n sub O. So n sub O is a subspace of n sub K. So when I translate it by G, I get some other subspace. I restrict this bilinear form, and now I can take the Clifford algebra associated with that form. So this is a sheaf of algebra whose value at a point is that particular infinite rank Clifford algebra. All right, so why did I do this? Or how does this connect back? So a feature of the perverse coherent T structure is that it's preserved by tensoring with vector bundles. Okay? So a feature of, we've kind of built this, maybe a clearer way to say what this twisted perverse T structure is about. We've modified things exactly so that it's preserved by tensoring now with the vector bundle whose C star weight matches its cohomological degree. And in particular, all the generators of this sheaf of algebras are of that form. So up to kind of infinite versus finite rank issues, this twisted perverse coherent T structure is preserved by tensoring with this sheaf of algebras. And that means that it makes sense to talk about module objects over this sheaf of algebras inside the heart of this twisted perverse T structure. And then the claim is that this is kind of concretely what the heart of this T structure looks like. It's the category of twisted perverse coherent sheafs of modules over this big sheaf of Clifford algebras. Any questions? All right, so to explain even a little bit more, and so now I'll try to circle back and be a little clearer about the terminology. So for to the trained eye, already as soon as I introduce this funny regrading, that already kind of makes clear that the role of causal duality in this. To spell that a little more precisely, let me recall the notion of linear causal duality. So this is a general kind of formalism study by Mirkovich and Risch. And so they studied the general setup that we're currently in. So you have some algebrogeometric object, let's call it X. You have a vector bundle W over that, and you have a pair of subbundles V1 and V2. And you study this derived intersection of vector bundles on X. And linear causal duality is a duality between coherent sheaves on that derived intersection and on the kind of natural dual derived intersection. So we can again take V1 perp and V2 perp. Those are by definition subbundles of W dual. So I can look at the derived intersection of V1 perp and V2 perp in W dual. So I have these two derived intersections for various, and linear causal duality is a duality between these two derived intersections and coherent sheaves on them. So there's a little bit of a quirk on the right-hand side, you'll notice on the kind of dual derived intersection. We actually want to shift everything by a cohomological degree of 2. Okay. So to draw out what that means now, and also to kind of be a little more explicit about how to think about these derived intersections. So let's start with the one on the left. I have the intersection of V1 and V2 in W. The coordinate ring of that I can represent as a differential graded algebra, which is a symmetric algebra on a two-term complex. And this two-term complex is a kind of evident one associated to these pair of bundles. You just look at, so I have, so this is a two-term complex of coherent sheaves on X, where V1 dual, that's again, sections of the dual bundle of V1. So just as a sanity check, the symmetric algebra of V1 dual, that's just the coordinate ring of V1, the total space of the bundle V1. And the coordinate ring of the total space of this derived intersection is the symmetric algebra of a two-term complex whose degree 0 part is V1 dual, but has a degree 1 part, which is V2 perp, together with its natural map to V1 dual. So V2 perp sits inside W dual, which projects onto V1 dual. So there's this natural two-term complex you can write down. The symmetric algebra on that is a representative of the quasi-isomorphism of the structure sheaf of this derived intersection. And then to depict that visually, so here I've drawn a grid that's showing that that's depicting what this algebra looks like, broken down by degree, by weight. And so just to be clear, the generators of this symmetric algebra, this two-term complex, they're depicted there. So they're in degrees -1 and 0, and then they're in weight -1. So that's a picture of the coordinate ring of one of these derived intersections. Meanwhile, this thing on the right, well, that's the picture on the right. So that's again symmetric algebra of a two-term complex, just the dual version of the one we write down. But because of this shift by 2, those generators are going to be way over there on the top right. And so this two-term complex is maybe even simpler to write. It's just V1 in degree 1, and the differential maps that via the natural map to W mod V2 in degree 2. So those are these two dual derived intersections, dual symmetric algebras. And then the kind of relation of the preceding slides to this slide is that this Clifford algebra is a kind of intermediate player between these two extremes. So if you look at the generators of this algebra, we have V2 perp and we have V1 with these certain degree shifts. And so that algebra, it's kind of like we just dualized, informally what we did is we just dualized some of the V1 dual generators on the left. And so the result is that we have this algebra, which is now kind of supported just along this rank 1 subgroup of this lattice that's depicted here, right? And again, there's a duality. This kind of duality is kind of mediated by a derived equivalence to modules over this Clifford algebra. So now we can say a little more, I don't know, explicitly or concretely, kind of where this terminology, kind of what's the connection to causality of this T structure? How is this name causal perverse justified? Well, really, so a sheaf on V1 intersect V2, that's a module, that's a sheaf of modules over that sheaf of algebras on the left. And so the heart of this T structure are those sheaves that become perverse after we apply this kind of intermediate form of causal duality here. So those are perverse coherent sheaves of modules over this middle algebra. Any questions?
Can you say what general feature of the situation allows you to use this intermediate? So you have this.
Yeah. So yeah. So the general statement is so essentially one always has this kind of picture, and really it's maybe even better to say there's a okay. So one always has this kind of picture. When I say there's a derived equivalence, there's the kind of usual subtlety of kind of completions and whatnot. But the way to kind of think about where that comes from. So how could you think about just normal kind of natural linear causal duality? If we think in terms of monads, you're saying you have sheaves on this derived intersection. You restrict to the 0 section. That functor is monadic, and the associated monad is that other algebra. Now, if you look at this functor here, if you compute the monad associated to this functor, that will be described by this intermediate Clifford algebra.
The zero section.
That's right. So you're restricting to the zero section ultimately, but you're only doing that after you've essentially forgotten the derived structure by pushing forward to one of the bundles. And you can see really that a more complete picture would be a kind of square, because I could also push forward to V2 and then do this restriction. That turns out to define the same T structure, but that's a kind of more complete picture. Any other questions? Okay, so let me conclude by circling back to the example that we discussed. So R C star C. And let me kind of try to do some computations in light of what we've discussed. So first, let me, so as we said before, so R C star C, it's this disjoint union of countably many components. Let me write the nth component as R sub n. And then let me write, so in this case, this is an sufficiently elementary case that one can write down all the simple objects, kind of do everything by hand. So here, let's write P sub n for just the structure sheaf of the classical part of the nth component. So if you like, again, we said that, say, a coherent sheaf on that nth component, that's a DG module over some DG algebra that we revisit on the previous slide. And I want to just look at the like the DG module where all of the degree -1 generators stack by 0, and then it's free on the degree 0 generators. So in this case, all of the irreducibles are just these objects together with this shift that we built in. So I can take I can take P sub n, choose some integer L, and then shift it by weight L and degree L at the same time. So those are all of the irreducibles. And then, so an easy computation, if I had told you the definition of the convolution product, which I didn't, but an easy computation would be that if you take the product of P1 and P minus 1 in the two possible orders, you get the two following answers. So first of all, each of these is going to be supported on just the 0 component. So the component over T to the 0. Again, that we're thinking of that's a affine derived scheme. And each of these products is going to be the structure sheaf of a particular closed subscheme. So in the case of the product of P1 and P minus 1, this will be the structure sheaf of, let's write this as Z1 minus 1. And this is just the subspace TO sitting inside O. So again, just to be clear, O here, let's see. So now O is the span of the red beads in the middle column over on the right. And then this is the codimension 1 subscheme that's spanned by T to the 1, T2 and higher. Okay, so it's a codimension 1 subscheme of the classical part of R0. And then the structure sheaf of that subscheme is this first convolution product. The other product is a kind of dual thing. It's the structure sheaf of the derived intersection. So this whole R0, that's the intersection of O with itself in K. This other convolution product, that'll be the intersection of O with itself now in T inverse O. So this is that's much smaller than K. It's just one dimension off. It's kind of O is codimensional 1 inside that. So if you like, that's a derived subscheme whose coordinate ring is generated by kind of all of the red beads and just the top blue bead there. So it has one generator in degree -1. Okay. So these are these two convolution products. And so as I said, so this is an example we saw earlier. So here, these are not isomorphic, but they sit in some closely related exact sequences. So to see it and kind of break down, to decompose this first product, well, this is just a kind of classical computation. So this is the structure sheaf of a codimension 1 subscheme in a big affine space. So it has a Koszul resolution, which is the top exact sequence there. So recall, again, P sub O, that's just some new notation we've invented for the structure sheaf of this of R0 classical, this big affine space. So I have a Koszul resolution whose first two terms are just two copies of that structure sheaf of PO. But the map between them, so that's the map corresponding to the to the bead T0. So that's a map that has some non-trivial weight with respect to this C star. So that's really a map from a weight shifted version of P0. So that's an exact sequence in the ordinary category of the ordinary abelian category of C star equivariant coherent sheaves. No, it's an exact sequence in the heart of the standard T structure. But that object over on the far left side, that's not in this new heart that we're actually interested in. So to get in an exact sequence in the heart of this interesting T structure, I should look at that weight shift and I say, that needs to be paired with the degree shift. So when I shift the degree of that, this exact sequence rotates as a triangle in the derived category. And now I get an exact sequence after rotating. Now I have an exact sequence that's really in the heart of this non-standard T structure. So the outer terms P0 and this bi shift of P0. So there's so now I have this this convolution product. It's not irreducible. I have this non-trivial exact sequence, but we've kind of explicitly computed in the basis of irreducibles. Meanwhile, I look at this other product, and what is that kind of explicitly? What's the structure sheaf of Z minus 1, 1? Well, it's basically the structure sheaf of the classical part of O, tensored with just a symmetric algebra on a single degree minus 1 generator. So that's just that's just a two-dimensional as an ungraded vector space. And so there's now, and that gives us a natural filtration. But now the kind of the sub part, the first term in that filtration comes from the kind of non-trivial part of that second factor. So we again have this exact sequence with the same outer terms, but they've been reversed now. So I have these two dual exact sequences. Again, this is in the cluster language, this implies that this tells that the classes of the PNs and these shifts endow K0 with the structure of a cluster algebra of type A1. So in cluster language, one would say this is an exchange relation for the A1 cluster algebra with a single frozen variable. So P0 is the monoidal unit, and then that frozen variable is P0 1 minus 1. Sorry, yeah. And okay, so those are some computations. But now, the way we did these computations, they look a little bit asymmetric. They kind of felt different in terms of the geometry, but that asymmetry kind of disappears once we kind of think in terms of this Koszul dual perspective. So now this kind of Clifford algebra, it's kind of a very simple case. It's just really a tensor product of two symmetric algebras. Now on, so I have infinitely many generators in bi degree 1, 1, and then infinitely many other generators in bi degree -1, -1. And these two simple objects, P0 and the shift of P0, as representations of this algebra, they're just one-dimensional representations, but in these different bi degrees. But now we can see that there's a symmetry between these two factors. And so there's an evident kind of dual extension in either direction. And these two exact sequences are just those dual extensions. And so again, that really ultimately comes from the symmetry between the red and blue parts of that picture, but that only becomes explicit once we Koszul dualize. So I'll go ahead and stop there.
Any questions from the room?
So does this monoidal category act on coherent sheaves on V?
Coherent sheaves on what?
On V itself, on the vector bundle.
You mean like the bundle V1?
Yeah.
I believe so. I believe so, yes. I don't have anything to say about it.
Can one characterize the T structure in terms of the action somehow?
That's an interesting question. I have no idea.
Okay.
Yeah.
So my understanding is that you produce a category and objects produce a canonical basis in the space of functions. And this is space, this is space of functions, some cluster Poisson variety, as far as I understand, at least in many examples.
In many examples, yes. We can't really prove a statement like that beyond the cases where we can compute by hand, which are very limited.
But is it? But then this basis is supposed to be parameterized by the tropical point of the dual variety. Do you see this?
Absolutely not. It's completely mysterious. The natural parameterization is this weight-co-weight parameterization, which is, I guess has the deficiency that it's completely canonical. Whereas, what you expect is also a bunch of non-canonical parameterizations associated to different clusters.
But it's supposed to be bijection between the tropical points of the dual space and elements of your basis.
I think the answer is I have no way to do that, other than giving a kind of stupid answer in cases where you can compute the cluster structure by hand, and then you can in principle infer it.
Do you see this Cauchy duality in terms of cluster structure? What does it say? Somehow?
It's hard. I don't think you can. I don't think I can really formulate an answer to that. It's kind of like you need to already be looking through the lens of this T structure in order to have a hope of seeing the clusters. So I have no kind of interesting answer.
Yeah, first just a quick comment. I think for the Grossmanian itself, there was also this paper of Finkelberg and Fujita who did the A case. So I don't know if their result is exactly special case of your result.
I think what they did was develop a completely logically independent, beautiful picture of the cluster structures on perverse coherent sheaves on GR GLN. And I haven't thought about potential interesting ways it could interact with the rest of this story, but I mean, certainly that construction is.
Yeah, and then another question is just to follow up on Sasha's question. So, or maybe just asking to clarify. So by dual here, we mean symplectically dual, which is, I guess, was.
I think Sasha means
this was the motivation for this BFN construction in the first place, right?
I think he means in terms of A versus X dual. So it's maybe let me kind of reframe a version of that question. You could also ask when do you expect, so okay, you have a bunch of monoidal categories. You're told to expect basically that these canonical bases give you some cluster structures. Are they A or X or something else? The answer seems to depend on the details of how you set up G and N. So the simplest example is already in the case of this is essentially written out in the Bezirkovnikov, Finkelberg, Merkovich. If you look at perverse coherent sheaves on GR PGL2, you'll get a cluster X variety. You look at I guess SL versus SL2, you'll get the cluster A variety in that type. So the A versus X is this kind of subtle thing that seems to depend on the details of what group you look at. So maybe that's some kind of context for how the answer to that question might emerge.
But then I have a different question. So is this related in any way to the symplectic duality?
I don't know. I mean, maybe that's a good question for Andy. One kind of obstruction to giving a good answer is that this is entirely a story about the four-dimensional Coulomb branch, and it's specifically not about the homology Coulomb branch. And so, symplectic duality is, yeah.
Yes, so I had a kind of related question to the one asked by Sasha Shapiro, which is that in some known examples where you can, as you say, compute the cluster structure by hand, does this Cazul self-duality have anything to do with, say, the cluster Donaldson-Thomas transformation? Or
the answer is no, but I can tell you what up to, like, this is a statement one can check in examples. Surely the general statement, the cluster Donaldson-Thomas transformation. This is good because I even wrote it on the slide, but then I forgot to mention it. So the fact that these monodal categories are kind of very specifically not symmetric opens up the possibility that taking double duals is an interesting autoequivalence of this category. And again, the phenomenon one observes in examples is that interesting autoequivalence is what decategorifies to the Donaldson-Thomas transformation.
Cool. Thanks.
Are there any questions from the room?
Oh, this guy.
Does the Higgs-Coulomb correspondence give you something on the Higgs branch side?
Sorry, can you say it again?
Using the Higgs-Coulomb correspondence, do you get a weight filtration on the Higgs branch also?
A weight filtration on the Higgs side?
Yeah.
No, and this kind of goes back to my perhaps disappointing answer to the previous question. Because we're specifically talking about the 4D Coulomb branch, that kind of obscures the connection to symplectic duality. So I'm not sure there's going to be a good answer to questions along those lines. Though again, other people might correct me.
Right. Wanted to ask again. You said something about double duals. Somehow I thought that you see Donaldson-Thomas transformations if you just take kind of this representation and that goes into the definition of RGN.
Oh no, sorry. I mean double duals. So this monoidal product is not a symmetric monoidal product. So the dual of an object with respect to the monoidal structure, the left and right duals don't necessarily agree. That's another way of saying it.
Hello. One more question. So canonical basis, which appear in the representation theory, classical linguistics. So this is this possible to make it part of this picture?
Probably one could. This is quite directly related to Ruben's question. So one thing that Finkelberg-Fujita proved in the case of perverse coherent sheaves on Gur GLN is that those bases essentially are the Kazhdan-Lustig bases in the appropriate sense. So under the appropriate isomorphisms.
No, I mean Lustig basis.
Sorry, Lustig basis.
It's more specifically Lustig basis in universal invariant algebra.
So I think the answer is made precise. The answer is known to be yes by Finkelberg-Fujita in pure type A. In cases where you have a quiver gauge theory, one can imagine an analogous statement being true. So that, and again, you can correct me.
So you say that in the case of AN, it's known.
In the case of AN, it is known by Finkelberg-Fujita. Yeah,
that's enough.
Okay. And the zero representation.
I just have a very quick question. So do you see cluster monomials appearing in your canonical basis for any reason?
Not in a more direct sense than the kind of implicit sense of you can, in some examples, very few examples, you can compute things by hand, see that there are natural clusters, and so cluster monomials are there. They don't play any particular special role in at any point kind of along the way there, I would say. Yeah. Thanks.
Any other question from the audience in the room? And anybody from Zoom, please feel free to unmute yourself and ask a question. Okay, if not, let's thank Harold again. We'll resume tomorrow at 10.
May I make a quick remark? So people want to see a product test, they may want to actually use them. Okay. Okay.